Okay. So I was wondering how you would do, alright, so here's the equation. 4x over x plus 3 equals 37 over x squared minus 9. All that minus 3. X minus, yeah, just minus 3.
Like this?
Yeah.
Okay. And I've written that correctly?
Yeah.
Okay. Well, what's the first thing we can think of to do that we can see in this thing?
Would you want to put 3 over x minus 9?
Yeah, we could definitely do that. So how do I do that? In other words, what's the common denominator between 3 and this fraction here?
X squared minus 9.
Right. So if I'm going to put that over an x squared minus 9, what has to be its numerator?
X squared minus 9 too.
Well, 3 times x squared minus 9, right? And then I'll erase this 3. In other words, that's the same number that we just had there. Okay? Now we can operate on the numerators that, what's our new numerator?
3x squared minus 27.
Okay? Be careful on this sign. Since this whole fraction is being subtracted from this fraction, you have to distribute that negative sign to all terms in the numerator.
Mm-hmm.
So it ends up being 37. In fact, let's start from 37 minus 3x squared, but then this is going to be a plus 9. You see why?
Yeah, that makes sense.
Okay, and it's all over x squared minus 9. Now we can simplify this. Let's add the 9 and the 37 together and get 46. Now we can do a couple of things. First of all, let me straighten out my fraction line. What's this called? X squared minus 9.
Difference of squares.
How does it factor?
X plus 3, x minus 3.
So if I write it like that, now I almost have the same denominators on both sides.
Mm-hmm.
What can I do? I could cross multiply, but I can definitely multiply both sides by an x plus 3 and get rid of both of those, right?
Uh-huh.
Now when I cross multiply, I don't have a cubic, I'm going to have a quadratic. And so, well, I don't really mean to cross multiply at this point. I need to multiply both sides by x minus 3.
Mm-hmm.
So what's on the left? Multiply 4x by x minus 3 and distribute it.
So you have 4x squared minus 12x.
And on the right?
46x.
Now put everything together. And, well, what's the next step? What are we looking at? We're looking at a quadratic, correct?
Yes.
Okay, whenever you have a quadratic, particularly one that has both an x squared and an x and a number, you always want to get 0 on one side.
Mm-hmm.
So let's move everything to the left, leaving 0 behind. What do you got?
I got x squared. No, 7x squared.
Be careful. I actually made that same mistake in my head as I was thinking about it. I thought it was going to be an x squared also. It's like that's a mistake that's just waiting to happen.
Yeah.
Okay. Now we got to factor it. In order to solve it, we got to factor it.
So you have 7 and 1. 7x and 1x.
Thank goodness there's only one choice there, because now what are both signs?
One's plus and one's minus.
Okay, but for me to write that, that plus minus might be different than this minus plus, because the difference of the coefficients. In other words, if these coefficients are different, 7 is not the same as 1, then you always have to allow for either way. There could be a difference.
Mm-hmm.
Now, factors of 46. Let's list them over here. What else?
23 and 2.
23 is prime, so I can't divide it anymore. I can't divide 46 by much, so that's probably our only choices. I can't think of any other factors. Okay, so what I always tell everybody is choose the two factors that are closest together.
So 23 and 2.
Yeah, and then you just kind of start from random. I'm going to start from 23 there and 2 there. And the one thing I'm pretty sure of is that I'm not going to be multiplying the 23 by the 7. Because that would produce 141x, and we don't see any numbers like that in the middle. So I almost have to have the 23 multiplier on my left. Okay, now what does that give us in the middle?
You have 23x and 14.
Minus 14, which gives you 9x. So if I move the 23 down to here and the 2 down to there, it's just going to change the sign and make it minus 9x.
Yeah.
So I can throw out that possibility. If I put the 23 on the right side and the 2 on the left, I know that can't work. So before we give up, let's try the other two factors, 46 and 1. Nah, no way is that working. 46 would have to go on that side, 1 would have to go over there. There's no way. I cannot factor this quadratic. So, how do I solve it? Once you've decided you can't factor it with integers, how do you solve it?
The quadratic formula.
Okay. What's the general?
I forgot the.
Okay, it's minus b plus or minus square root of b squared minus 4ac all over 2a. And if there's anything you should memorize, it's this. Because it's not going away. You're going to be dealing with it for a number of years. So, in our case, what is A, B, and C equal to? What's A?
A is 7.
B?
Negative 12.
And C?
Negative 46.
Okay, so let's plug in. Minus B?
Negative 7. No. Positive 12.
Plus or minus the square root. This is called the discriminant. It actually has its own name, what I circled there. And the reason it has its own name is because frequently the first step in solving a quadratic is to figure out if the discriminant is positive or negative. The reason being is that if it's negative, then we only have imaginary solutions for this. There are no real solutions. If it's positive, we're going to have real solutions. So a lot of times the first step I'll do is figure out what the discriminant is. Well, in this case, I've already kind of done it in my mind and I know it's going to be positive. But what is it? Let's see. So it's b squared, that's 144, right?
Mm-hmm.
And then the way I suggest you do this every time is this way. No matter how simple A and C are, go ahead and write them in there. And the reason is that frequently C is negative. It's the only way that it makes the whole thing positive. And as long as you write it in like this, you're not going to make the math error. Notice that this is subtraction, that's a negative sign. And it's real easy here to do two subtractions accidentally. So what I also tell everybody to do is do this calculation next in your calculator before you do anything else. What do you get?
I don't have a calculator on me, I'm sorry.
Okay, let me turn mine on. Yeah, you should probably always have your calculator.
Okay.
4 times 7 times a negative 46 equals minus 1288. So that I can erase with minus 1288. And the reason I said do that one first is because this is always a subtraction sign. So if C is negative, this is frequently negative, and now you're adding those two numbers. Okay? Mm-hmm. And those add to 2232. No, excuse me, 1432. So I can replace the discriminant with 1432. Why are they giving you a problem that has such hard numbers? Just, they like doing that?
Yeah, they do.
Okay. Let me see what the square root of 1432 is. Because the disadvantage of hard numbers is it makes it really hard to simplify.
Yeah.
Hold on. It's the square root of 1432. It's probably a whole number, but no. It's 2 root 358. Well, how about that? Because they simplified it for me. Right? Do you have an Inspire?
No, I don't.
Well, they're nice. When I put in root 1432, it gave me back 2 root 358, which means that cannot be simplified any further.
Mm-hmm.
Now, how do you simplify that? There's one last simplification I can do.
Would it be make the 12, simplify the 12 into 14?
What can I divide top and bottom by?
2.
And that's it. So I'm going to divide that by 2, I'm going to divide that by 2, making it a 1, and I'm going to divide that by 2, making it a 7. So our final answer is 6 plus or minus root 358 all divided by 7.
Okay.
What a strange answer. Should we start the problem right? This was the original problem?
Yeah.
Okay.
I believe we did it.
Yeah, no, I'm thinking, I don't know, that answer is just so strange that I feel like I made a mistake somewhere. But if we did, we did. There's no point in going back over and looking for it. Is this material that you have to put an answer and turn in?
No, no.
Okay, this is just strictly review material. Okay. Let's go on to the next one then, and assume we didn't make a mistake. But...
Okay, so just looking through right now.
Uh-huh.
Could we go over this one's a little? No, that's way too simple actually.
Yeah, ones you know how to do are 100% certain that you know how to do them. We don't need to go over those.
Yeah. Could we go over? Just for like review's sake, could we go over this one? 8 over x plus 3.
No, that's not all of it.
Yeah. Equals 5 over x minus 3.
What's the easiest first, well, yeah, what's the first step here?
Would it just be cross multiplication?
Yeah, so what's the new left?
8x minus 3.
8x minus 24. If you're going to
Sorry.
Yeah, if you're going to cross multiply, then you need to multiply the whole thing. Equals what?
5x plus 15.
Okay, next line.
So it should be 3x equals 30. No. Yeah, 39.
So
That should be 13.
Uh-huh.
Alright. There we go. We go to the back of the book now to other problems.
Okay. We're doing an hour today, correct? Till 4?
Correct, yeah.
Okay. I thought that you had 2 half-hour sessions back to back.
Yeah. That's what it is. Could we do this one? It's 8 over x squared minus 49.
Difference of perfect squares. Keep going.
All over. Sorry, I just lost it. 5. Over 3x squared minus 21x. Minus 6 over x minus 7.
Hold on. I'm a little lost. All still under the second fraction bar?
Yeah.
Minus what?
Oh no, sorry, not all over. It's a separate fraction.
Okay. Minus 6 all over what?
X minus 7.
So that's what we're looking at?
Yeah.
Okay. Always, well, maybe not always, but we got to take care of the more complicated part first. And that's the denominator.
Mm-hmm.
So probably the first thing that makes sense to do is factor a greatest common factor out of this. What's the greatest common factor you can factor out of that expression?
Greatest common factor. 3.
3x, what's left?
X minus 7.
Okay, notice there's an x minus 7 over there.
So you just have to multiply the other one.
Reasons we did it, yeah. So we have 5 over that. Now we have to find what in the bottom? How do I subtract that term from that term? Because that's what we have to do next.
Don't you have to multiply that term by so 6 over x minus 7 times 3x over 3x?
Good. In other words, we have to get a common denominator, right?
Yeah.
And the common denominator is that. We don't have to multiply that whole thing by that whole thing to get a common denominator, because this divides evenly into that. So you're right, is all I have to do is get this common denominator set up properly, and I'm going to do that by putting 3x over there and 3x down here. Now I have a common denominator, and I can operate strictly on the numerator. So what's the numerator become?
5 minus 18x over 3x minus 7.
Yeah, 5 minus 18x. Did I do that right? Yeah.
Wouldn't you just cross multiply it at this point?
Well, not cross multiply, but
switch the fraction and then
yeah.
multiply.
In other words, once we've gotten it to where we have a fraction over a fraction, now we can flip and multiply. You can't do it as long as you have two terms in the bottom. In other words, I had a minus 6. So the bottom started out as two fractions. You've got to turn them into one fraction before you can flip and multiply. So if I flip and multiply, here's what I'm going to be looking at. Now what can I do to the top left denominator?
Can't you cancel because you have x plus 7 and x minus 7?
Right, you have to factor. In other words, the difference of perfect squares is going to factor into x minus 7 times x plus 7. And now you can cancel, and you're left with whatever you're left with. What is that?
There'd be 24x over...
Should you multiply them together or leave them factored?
Leave them factored?
Yes, always. If you multiply those two together, you're just going to have a quadratic. And the reason factored is better is because let's say I needed to take this answer and multiply it by something else. Well, maybe the something else has one of these factors, and in other words, then I would have to factor it to go to the next step. So I always like leaving all my answers factored.
Yeah. So I'll start doing that then.
All right. And there's not much I can do there. Now, let me just review one principle here. Every time you've canceled a linear factor with another one, it's been the same one, right?
Mm-hmm.
What if I had this? Can I do anything?
No.
Actually, you can. That's the one case where you can cancel them but it's a minus 1. And notice why, because 7 minus x could actually be written as minus x minus 7. Notice that if you distribute that negative sign to the bottom, you end up with 7 minus x. So that's the same, and now I can cancel that with that, but I still have that negative 1 left over. So just keep your eye out for that, because that's the only time you'll ever see anything hard with any one of these problems, is if you get an a minus b over a b minus a. Always make sure you cancel that to a minus 1.
Okay.
All right. What else?
This is kind of like my own question. So suppose you have x over the square root of y. How would you solve that so there's no root?
That's it.
But isn't there not supposed to be a radical in the denominator?
Well, okay, you could an irrational number. Yeah, you could rationalize that if you want.
Yeah, because it's got some questions like that. So
yeah, no, that's fine. I'd love it when you ask questions like that. In other words, that's the officially correct answer. But y doesn't necessarily have to be a non-perfect square. In other words, if y is 4 or 9 or 16 or 25, then we don't have an irrational number in the denominator. So I'm not sure that that's always an automatic step. This answer over here is the same as what you started with. It's exactly the same. But the one guarantee is that as long as y is an integer, this has a rational denominator. The whole reason for not having an irrational denominator is I believe, one more of philosophical than necessarily mathematical. In other words, the whole process of division. I can divide a number by a number. I'm splitting up 4 into 3 equal parts, right? But how do you divide 4 by an irrational number, by a square root of 2? Because what is square root of 2? You can't say I'm dividing 4 up into square root of 2 parts. It doesn't make as much logical sense. And so mathematicians, for as long as I can tell, have always insisted that if you're going to divide by something, divide by a rational number. And so they turn these into so that's the same as that. It's amazing how frequently they look substantially different. All right. What else? When is your test?
It's tomorrow.
Okay.
I'm trying. I found this really hard. Here it is.
Okay.
So solve the equation 3 with x plus 2 as the power equals 9 with x plus 1 as the power. How would you solve that?
By finding a common exponential base between 3 and 9. What is that common exponential base? 3. Okay, so I can write 3 to the x plus 2, and over here I'm going to call this 3 squared instead of 9. And I'm going to put it in parentheses like that. Now I still have my x plus 1 power, but now I have some rules of exponents. In other words, I got 3 to the x plus 2 over there. Apply the rules of exponents. What's that equal to?
3 2x plus 2.
Now, if you have one number to an exponent equals the same number to a different exponent, you can equate the exponents. The exponents have to be equal. What's that give you for a solution?
X equals 0.
And let's test it. If I plug in 0, I get 3 squared equals 9 to the first, which is a good solution. Now, these can get a little harder, and if there's anything I remember about your stuff is they tend to throw in the hard problem every now and then.
Yeah.
What if I said this? Now what is the common base between 9 and 27?
Would it be 3 still?
Yeah, very good. It's not 9. Most people would tend to, they'd want to make this 9 and they'd want to make this 9 times 3 because they're used to factoring. But when I'm looking for a common exponential base, I've got to be able to write each of these numbers according to that base. Well, 9 is 3 squared. 27 is 3 cubed. And now I apply the rules of exponents and I get and now again I can equate the two exponents. Those two have to be equal. So you get x equals 7. So it's the common exponential base is not always going to be one of these two numbers. A lot of times they'll give you like 4 and 8. What's the common exponential base between 4 and 8?
2.
Yep. All right. I think you got those. You know what this number is?
Would it be 27 to the third power?
No, it's 3 to the 27th power, which is an enormous number.
Wait, how would you get 27 out of that?
Because you always start from the top down. In other words, you take 3 to the third, which is 27, and then you have 3 to the 27th.
Oh, okay. So you basically go down.
Yeah. In other words, it's not clear what you would do here. But I'll bet you very few people would think that that's more molecules than exist in the universe. That's how big that number is. Yeah. No, it isn't that big. 3 to the 27 is a big, big number. It's like 12 trillion. But, yeah, now this is a completely different problem than that.
Mm-hmm.
I put parentheses around it. Now I apply the rules of exponents, and that's equal to 3 to the 9th, which is not a small number, but nowhere near to 3 to the 27th. So the absence of parentheses matters a lot here. But the only reason I mentioned this is I was reading an article about how large of a number can somebody think of. And they use this notation. This notation is written like this. And there were certain rules. You can't just say, okay, I'll take that guy's number and add 1 to it. You also couldn't answer infinity. Had to have some useful purpose. But what I found interesting is that it was 3's used with a whole bunch of arrows. And they had some exotic. They had like 57 arrows in a row, which of course means 3 to the 3 to the 3 to the 3 57 times. I mean, it's pretty amazing how big of numbers that have a usefulness, how big they are.
Mm-hmm.
But
it's a big number.
Yeah, not to deviate from your stuff. What else you got? even of his
So,
questions.
for this 91, it's line. Is it ln? What does that mean? Is that just
Natural log. ln, like that?
is it because it has a base of like a e?
Uh-huh. Same as that. That's what ln is equal to. Is log base e. What is e? Well, e is one of those irrational numbers. It's approximately that. Goes on forever, just like pi, never repeating.
What's its purpose?
There are a multitude of real-life situations that grow based on this number. For instance, bacteria in a petri dish, populations of rabbits or humans, radioactive material decays based on this number, money in a bank appreciates based on that number. That number, in a nutshell, I'll define it for you very quickly and let you think about it for a second. I know you don't know what limits are, but if you took this quantity over here and you let x approach infinity, in other words, keep getting bigger and bigger and bigger and bigger, what number would you think it would go to? Notice that inside the parentheses getting closer and closer to 1 as x gets big. But you take that number that's closer and closer to 1 and you're taking it to a power that keeps getting bigger and bigger and bigger. So it's not real clear whether this number would go to 1 or would it go to infinity or would it go to somewhere in between.
So it's kind of like a paradox.
Not really. It goes to the somewhere in between. Guess where it goes to?
2.7.
E. And this is what happens with all of those processes. Like interest rates. It's 1 plus some rate taken to a power some number of years. And that kind of matches that. And like I said, it applies to so many things in the world that E is without a doubt the second most important number in math. You get into calculus, yeah, pi's maybe number 1. But you get into calculus and everything is done with natural log pretty much. And natural log is, of course, based on E. It seems an odd thing to be the perfect thing to use with calculus, but it is.
That's cool.
Yeah. And how would you use natural log? Well, what if I gave you this problem here? Solve that.
Would you make it natural log with 5 equals x?
Well, first of all, I'm going to take the natural log of both sides like that. Next of all, I'm going to take the x and put it on the fraction line because that's a property of logs that I can use. And next, I know that that's equal to 1. Whenever the base is equal to the argument, that whole thing is 1. So yeah, what you said was correct. X is equal to the natural log of 5. Whenever you have an equation where your variable is in the exponent, you're going to have to use logs. You and I have had a session on logs, haven't we?
Yeah.
You feel comfortable doing log problems, solving log equations, and solving exponential equations? This is an exponential equation. There's no algebraic way to solve it. Only way to solve it is using logs. And then looking up what that log of that number is, what's the log of 5 or the natural log of 5? Well, I got to get that out of my calculator or out of a textbook. They used to have tables in the back of math books that gave you all the natural logs of any number you could think of. Not kidding, they did. And they also had trig functions. In other words, they had sine and cosine and tangent tables also.
So this was before calculators?
It was before calculators. It was like in the late 60s. And yeah, it was, calculators changed the name of the game for sure.
Yeah.
Especially for graphing. Back before calculators, graphing was a giant pain. If you needed to, and that's why learning math is actually so much easier today than it was when I was in high school, because we didn't have graphing calculators. You couldn't really depict functions in a graphical way very easily. I mean, you could graph something, but you had to make a table. You had to make an XY table of points and connect the dots. So you couldn't graph stuff easily. And
yeah.
Without being able to graph stuff, it really does change the way you understand math and the way you learn math.
Because you don't see it visually.
Yeah, exactly. So I wonder 100 years from now what new thing they will technologically develop that'll make it easier to learn math. Unfortunately, I think we're going the other direction now. But
the phones.
Well, no, we have calculators that'll do pretty complex calculus.
Yeah.
So you don't have to ever really know how to do it by hand or manually. And it just keeps going in that direction. So at what point will humans not be able to do complex math? And they'll have to rely strictly on calculators.
Would that be a good thing or a bad thing?
I think it's a bad thing because, well, it goes beyond that. It's not always doing the calculation in a calculator as much as setting up the problem. And in order to set up the problem, you have to kind of have the intellectual training on how to do the calculus. So
yeah.
If you didn't learn how to do, it's like expecting somebody who never learned their times tables to be able to solve an algebra problem. Maybe with the help of a calculator, but it sure makes it a lot harder. And
yeah.
I think that's true with all higher math, and that's why they insist upon forcing you to still learn how to do it, even though you can put it in a calculator and get the answer immediately.
That makes sense, actually.
Yeah, no, well, same thing with arithmetic. I mean, they should force everybody to learn arithmetic, and yet I got students that have made it to pre-calc, and they still don't know what 7 times 8 is without the use of a calculator. I had a girl once that I said, the question was multiply this number by 10. You know what she did?
What?
Reached for her calculator. Uh-huh. Yeah, that's when you know things have gone terribly wrong. So what else you got, Jake?
Yeah, let me look.
Because you're doing a whole semester's worth of stuff, aren't you?
Yeah, in trimesters.
Okay. So the fact that you're having difficulty finding stuff is probably a good sign, huh?
Yeah, it is a good sign.
Because you're not giving me anything that you already know, and you're having a hard time finding stuff that you don't know. Well, that is a good sign.
Yeah. I took like most of yesterday to just study for this, so I think I'm good for the most part.
Okay.
Let
me give you a log problem.
Okay.
You solve that for x.
So first you'd condense it.
Okay, into what?
Log base 7 x squared minus x equals 10. And then,
Let me make this not 10. What do I want to make it? Let's see. Hold on a second. I got to think in advance here. 10 is not a good number to use. Let me use, and 7 is not a good number to use. Sorry about this. Not going to change anything. Let's see if I can get that to be 6. Okay, now what? In other words, the only thing I changed were stuff you didn't need. You did the hard part. Now how do you solve it?
Would you make it 6 to the 1 power, so just 6 equals x squared minus x.
Okay, keep going.
And then you subtract 6 to make it 0 to solve. And then, so it would be x, yeah, x in both of them, plus and minus in one. And then it would be 3.
3 goes which sign?
I'm trying to figure out.
3, the bigger factor always goes with the sign of the middle term.
Okay, so it would be negative.
The term is minus, so the 3 is going to go there, the 2 is going to go there. Mm-hmm. So now what are your solutions?
You'll have 3 and negative 2.
Are both of those valid solutions?
Do I have to put it in and find the extraneous answer?
Yeah, see, right. In other words, there's 3 things that produce extraneous answers. Radical signs, absolute value signs, and logarithms. So when you have a log problem like this, particularly where it results in a quadratic that you had to solve, almost always one of these solutions violates the domain. What's the domain of that?
All real numbers?
No, positive numbers only. You cannot take the log of, not only can you not take the log of a negative number, you can't take the log of 0.
Mm-hmm.
So the minus 2 we throw out because it violates that domain. And most importantly, you have to go back to the original problem to check domain. You can't check this part for domain. Notice that it doesn't violate the domain here, right? Mm-hmm. In other words, minus 2 squared is 4, minus 2 is 6. So when I plug it into this part, I'm not violating any domain at all with either answer. So that's kind of an important realization in that it tells you that these 2 things are not precisely the same. This is a rule of logs where we can expand and compress, but it does some funky things to our domain. And it allows you to get some domains by that would never get by that. And so always make sure you go back to the original one, because this will frequently be the case. Because once it's squared, then all those negative numbers turn positive. So on a test, the only answer for this one would be x equal 3.
Mm-hmm. Could you plug it into the quadratic equation or no?
I'm sorry, what?
Could you plug it into the quadratic equation?
Well, the quadratic equation is used for factoring. Mm-hmm. That's the only thing you use it for. if I could not have factored that easily, in other words, make this a 5 instead of a 6, now I got to use the quadratic equation to factor it. And I'll find out which are my positive solutions and which are my negative solutions. Well, the negative solutions you wouldn't be able to use. Because any x that comes out negative violates that domain. But that's why it took me a while to think about this as to what base is going to produce a quadratic that I can factor. Because certainly not all quadratics, in fact the average quadratic you're not going to be able to factor. Like this one. Except using the quadratic formula. And notice the quadratic formula has that plus or minus, so you're always going to get a plus solution and generally a negative solution after doing all of this. So whether you're able to factor a quadratic, notice that factoring a quadratic gives you exactly the same answer as the quadratic formula does. I could have applied the quadratic formula on our original problem that had a 6 there. I would have gotten exactly the same two solutions, minus 2 and plus 3. The only thing is it's harder and longer and you got to remember it, and so if a quadratic can be factored, that's always the way you do it.
Okay. Hang on a second. I'll be back.
Okay. Do you have to have all your general equations memorized, or do they give you those in the test?
They give me those.
Okay.
And so I had somebody at the door, so.
No, that's fine. That's fine. I was just thinking of what we can cover in 5 minutes that might be helpful to you.
Sorry. Looking through the review.
Give me subject matter. In other words, logarithms you covered. Radicals. How about simplifying radicals? Are you good at that?
Kind of.
Simplify that.
So you take 4 out, so you get 2. So then you'd leave like 2 out and 20 in, and then you could take 4 out again. So you should get 4 with square root of 5.
Good. Could have factored a 16 out immediately.
Yeah.
If you see it. Not that everybody would see it, but that's 16 times 5, which immediately gives you that. So the secret kind of is to find two factors where one of them is a perfect square and ideally the largest perfect square. In other words, if I'm factoring 200, there's lots of factors that are perfect squares that go into that, but 100 is the biggest one.
Yeah.
So that's 10 root 2 immediately. All right. Jake?
What about functions like f of x and g of x?
Okay. F of x is just a different notation for y. In other words, if I have a linear equation like that, I can use this notation, and it's a little more powerful. And the reason it's more powerful is because now I can ask you, well, what's f of 2? What is f of 2?
7.
What's f of x plus 1?
3x plus 3, so 3x plus 4.
Yeah. Notice that I can't do that if I'm using y notation.
Mm-hmm.
And having this ability to substitute something other than x ends up being very powerful also in calculus. So f of x notation is just better than y notation. And g of x merely means a different function. That's all. Just I'm going to call it g, and it's not going to be 3x plus 1 because that was f of x, but maybe g is x squared. Okay? And the other power of f of x and g of x is it tells you what the variable is on the other side. If this was an r, then it wouldn't be a g of x. It would be a g of r. So whatever's in the parenthesis tells you it's a function of r or a function of x. And then if I use something other than x, I'm saying evaluate that function when x is equal to 2. Or when instead of x, let's evaluate f of x plus 1. Now, your question might have had to do with inverse functions. Have you done inverse functions?
Yeah, we covered them a little bit.
Okay. Unfortunately, I do have a 4 o'clock session, so I'm not going to be able to cover them, but they can be challenging, although not really. There's 2 rules to find the inverse of a function. Switch the variables and solve for y.
Okay.
You know what I mean? In other words, if I give you this as my function and I say find the inverse of it, first step, switch the variables. Second step, solve for that y right there. So that y is going to be x minus 1 over 3.
That's pretty.
And that's the inverse of that.
All right.
All right. Jake, have a good one. Good luck on your final.
All right, well, thanks.
I might not talk to you again for a while.
Yeah. Well, thank you.
Maybe next year. What are you taking next year?
Trig and precalc.
Okay. Think of me. Talk to you next year.
Yeah, see ya.
Okay, bye-bye.
Bye.